Hello, welcome to Dubeke Consult. Our custom here is picking any piece of architectural drawing. Then, as a team, we work together to produce a detailed working drawing that can be easily understood and implemented on site. This is the structure we've been working on for a while, and we've been able to push this from the general arrangement to the analysis and design phase. Today we'll be looking at how we can design a raft foundation to support this structure. We understand that the reason for you choosing to design a raft foundation might be different from ours, which can be as a result, but not limited to, the soil bearing capacity of the site, the magnitude of load coming on the structure, and cases where we have closer columns. So when trying to design for a pad base, we will have interfering bases. Whichever the case may be, the principles of raft foundation design you'll be exposed to in this video will help you counter these issues, and we'll try our possible best to ensure we do not choose members that will pass our design at the first instance. So when you encounter similar issues while making your real life design, you can also look at the possible solutions and resolutions to such issues. To see how we are able to model, analyze, and design up to this level, I will leave a link in the description so you can go through. And if you find this video helpful at any point, do not forget to like, subscribe, and turn on the notification bell so you get notified anytime we post new videos on our channel. Heading on to design your raft foundation, there are a few important checks you need to make. Firstly, you have to ensure all your floor slab on the model has been analyzed and designed. You also have to ensure your beams on all levels has also been analyzed and designed, knowing fully well that the slab load will be transferred to your beams and the beams will in turn transfer this load to your columns. So you also have to ensure your columns, which will have direct contact with your substructure, has been analyzed and designed. To design our raft foundation, let's head on to our story 0. Okay, so if we click here, this is actually the foundation level. So this is our story 0, and at this story 0 we have no other elements except our structural columns. Okay, so for the fact that we are designing this with a beam raft foundation, first we need to connect these column points with our beams in order to create a rigid frame for our slab to be suspended on it. All right, so we'll connect all these columns with a beam, and we also have to make sure or try our possible best to ensure our beam arrangement at the ground floor also matches with the beam arrangement on the first floor, except in cases where we need to make alternatives. All right, so let's head on to story 0. Then we'll come to window and we'll click on arrange windows. Okay, so we can work hand in hand. Let's tie 2 windows together. All right, so now we have our 3D view here. We have our ground floor plan here, and we have the 3D plan here. All right, so I will come to this 3D, then I will make this a plan as well, but I will leave this as story 0. Then for this one, if I click on this window, I will take this to story 1. Okay, so we can be observing our beam arrangement on this very level and implement it on this other level. All right, so to insert our beam as usual, what we need to do is we'll come to this part, or we'll come to concrete members, then we'll click on concrete beam. Then we have our beam parameters over here. For the width of our beam, which is 230 millimeter, we'll ensure it matches with the width of our column. Okay, so we will ensure this width and the width of our column matches together. So we'll leave this at 230 millimeter. While for the thickness It all depends on the various factors like the water table of the site, or let's say that they intend, or you intend to raise this structure to a specific level on that very site. You can also get that information. Or during the soil investigation, it was advised that we raise the foundation to 1.5 meter above a specific level. So this is the factor that can affect the depth or the thickness of your beam. Okay, so for this very design, we'll be adopting a thickness of 1.2 meters. So I will type 1200 over here. Then I will place this column to column. All right, so I'll start from here to here and here. Okay, so let me come to this part and observe the beam arrangement. So I'll come back to this story, right click, come to properties, and I'll try to copy what I have on this other part. So I'll put this here. I'll put this here as well. Okay. Then I will continue because we've gotten to this part. So I will continue from here to this one. Okay. It is advisable that you place these beams from column to column, all right, especially when you are designing a raft foundation or cases where you have interconnected grids. So you don't put these beams on the grid you do not intend to put them. Okay, so I will stop this here. Then I will create this from here to this part, all right, to here, then finally to this part. Okay, then the next is I will take this here and here. All right, so this runs to the end, so I can take this beam here, then I run the perimeter beam to this part. Okay, so let's take a look at what we've done so far. If I close this and I right click on this and come to my 3D view, you will see the perimeter beams around this area has been created from the column to the column points. All right, so let's come back and finish up the creation of beams. So I'll click on this, right click, and take the properties. Then this goes from this point to this point. So I will click, take the properties, and draw this from here to here. All right, okay, so if you observe this other grid, you will see that when we get to grid Y10, it actually stops, this beam actually stops here. All right, but in order to create a very rigid frame at the foundation level, we'll have to connect this beam from this point to this point, so we can have this as one panel and we'll have this other one as another panel. Why this will serve as another panel? This is just to enhance the rigidity of this level, so we don't have beam resting on beam. We can have beam connected directly from the columns. All right, so I will click on this and take the properties, and I'll draw from here and go straight down to this part. Okay, and I'll do the same for here. So I'll draw from here and position this at this part. All right, so that's it. Then we'll take same principles to the left hand side. So we'll draw from here to here, and we'll also draw from here to this part. Okay, and the next is from here to this, and we can take a look at what we've done so far. All right, so this is what we've been able to create so far. So let's head back to our plan view and quickly let's close this up. We'll come to properties, then we'll insert the beams on the y-axis. We'll take from here to here. Okay, so we'll take from here to the end here, and in this case we'll connect this to this, and we'll also connect this to this. Why? We can connect from this column to here and connect from this column to this part. Okay, so we'll use the same principles here. I will position this here, then we'll click here, and we can put this over here, and the next is this column to this column, then this to this, and from this point we can join this point up and also join this to this part. All right, so the next is connecting these other aspects. So we'll draw from this grid to this grid, and for this part the building also stops here. Okay, so we'll also draw, do not forget that there's a shear wall at this part, but we'll also have to draw a beam. Okay, maybe this is not, will not be affected during construction, but for us to put a slab over here, for us to slab this part, there has to be a beam. So we'll put a beam at this region. So we'll click from here to here. Okay, and we'll also click from here to here. All right, then the next is we'll connect this to this, and finally we can connect this one to this and here. Okay, so we've successfully created the arrangement of our beams in order to receive our slabs. Okay, so let's take a look at what we've done so far. If we right click here and come to 3D, so this is what we've been able to achieve so far, right? So the next step is creating our slabs to be at the level of these beams. So permit me to put this to a single screen, and let me take this to a single screen. Okay, all right, and let's go back to our plan view. So to put our slab on this very structure, we'll click on our slab. Okay, this is our slab icon. Then we'll assume a thickness. The minimum thickness you can assume for your slabs at when you are designing for a raft foundation is 200 millimeter. But for this design, we'll be adopting a thickness of 250 millimeter. And due to the fact that it will be at the foundation level, so it's exposed to soil and probably other chemicals that might be at the ground level as well, we'll increase our concrete cover to 30 millimeters. Then we'll come to the loading tab, and we'll leave this at an imposed load of 1.5 and dead load of 2.2 kilonewton per meter square. And we'll put this here, and let's close this up. Okay, because there's something I want to show us. So if we come to our 3D view, you will observe that this slab that we've inserted on our beams is actually at the bottom of our beams. Okay, it's actually at the bottom of these beams, but we need to take this slab up to flush with the top level of these beams, unless except you are designing for an upstand beam, or except you are using the upstand beam system of beam raft foundation. But for this raft foundation, we are using a downstand beam, so the beam will have direct contact with the soil and not the slab. Okay, so we'll come here, come to plan view, and we'll click on this part. We'll click on the slab, we'll right click, come to properties, then we come to this loading tab. Okay, on this loading tab there is an option here for relative level. So our relative level, if you intend to take this to the level of our beam, we have to subtract the height of our beam from the thickness of our slab, and the height of our beam assumed is 1.2 meters or 1200 millimeter, while the thickness of our slab assumed is 250 millimeter. Okay, so if we subtract that, and we bring up our calculator, if we take 200 from, if we take 250 millimeter from 200, sorry, 12 minus 250, this should give us 950 millimeter. Okay, so let's minimize this, come here and take our relative level to 950 mm. Then we can update this and we close. So let's head back to our 3D view and see what we've done. So as you can see, this is now flushing with the level of our beam this is now flushing with the level of our beam. So let's come back to the plan view. Then we'll click on this very slab. We'll right click, come to properties. Then we'll adopt the properties of this slab on every other slabs on this very model. Okay, so we'll click here and we insert in between these grids. All right, so just click in between the beams and your slabs will be inserted. All right, so we've successfully inserted our slabs, and let's have a look at what we've done. So the total perimeter of our foundation has been covered with the slab. Okay, so let's take a look at the design principles of this Raft foundation and how we intend to transfer this load coming from this structure successfully to the ground. All right, so as we know, our slab load will be transferred to our beams, while our beams will in turn transfer to our columns. Then our columns will transfer to the, from the superstructure we transfer to the substructure. Then at the substructure level, we have both the beams and we have the slab. So if we come to, on getting to the slab, on getting to the superstructure, the magnitude of load that is coming from our column, there will be high magnitude of punching shear. So our beams will eliminate that punching stress that is coming from the superstructure due to its effective depth. Because if we are to leave our slab of 250 millimeter to counter the punching stress that is coming from our column, then we will definitely have our slab failing in punching. All right, so our beams are here to not just to create a rigid frame for our slabs, but in turn eliminate our punching to, all right, due to its thickness. Now, when this column is acting on this substructure, it will push this foundation downward. And we also have our earth pressure that is also trying to push this slab up to, it also try to cause this slab to fail. So it will also be pushing the slab upward, all right? And we have to design our slabs in order to resist this earth pressure. And after resisting this earth pressure, it will now transfer this load down to this beam. So the soil has to be firm enough in order to receive that load that is coming from the beam. And if our beam is not okay, if it's not designed sustainably, in order to transmit this load to the surrounding soil, let's say we have a very weak soil, we can as well create something like a cantilevered footing. Okay, this is also referred to as an apron. So we create a cantilevered footing in order to increase the base of our beam and in order to transfer this load to a larger surface. All right, so we'll be exploring this option. If we successfully design our slab and we transfer our slab load to our beams, then our beams can also transfer this load to the ground successfully. We do not have any issue at all. But if we are not able to transfer this load, then we'll create a larger surface or a larger area for our beams in order to transfer this load. Okay, so let's go back to our Prota and we'll kickstart with our raft design. So I will come here, right click, come to my plan view, and as you know, in order to design our raft, our slab, we need to first run the strip across these slabs. All right, so what I will do is I will come to strip and we'll start from the x-axis. We'll start from this x-axis here, then we'll move on to the y-axis. And if you are trying to design a slab for the foundation level or a raft slab, you will use your finite element strip or your FE strip. Then we also get to observe the boundary conditions of these very beams, okay, of these very slabs. So this first grid, our boundary condition here, you have a beam at the edge and we also have a beam at the edge. So for every slab on this very foundation level, we have beams surrounding it. Okay, so we start at bulb and we also end at bulb. So we'll click on this part to draw our first slab strip and we hold our control. In order to understand how you can draw this, you can also go through our previous video on slab analysis and design. You will see step-by-step processes on how you can draw this strip. Okay, but we're a little faster in this case. So we'll draw from beam to beam and hold your control button in order to create a straight line. So we'll also draw this, then we'll draw this, and we'll draw this. Okay, so from this little slab over here, we have it spanning from slab to slab. Okay, so we can draw from here to here. All right, so for the next one is on our y-axis. So we'll come to our y-axis and we'll click on beam to beam due to this boundary condition. So we'll click here, hold the control and click here. The next is we'll go from this point up to here. We'll draw from here to this part. So now we have our slab strip across both the x and the y axis. Taking the next step forward, we need to ensure we've selected the desired reinforcements we intend to use for our slab design. Okay, so let's come to analysis Then we'll come to building analysis. We'll allow this project to save. And over here, we'll come to edit materials, okay? So we'll come to the foundation level. Our FCU will be going with grade 25/30. Then our rebar diameters, we'll unselect all of this and we'll select Y12, and probably the worst case scenario, we also select Y16, okay? So this is okay. Our links is Y10 only, so this is okay. Then we can close this up. All right, so the next is running our finite element raft foundation analysis. And to do that, we'll come back to analysis and we'll come to finite element raft foundation analysis, and I will click on raft foundation mesh and analysis. So it will take you to this place and you click on generate model. So it will actually generate a mesh around your model that will be used during the analysis. All right, so this is our mesh. So we can, when the mesh has been generated, you can close this up and allow it to take you to your post analysis tab. So here at the post analysis tab, we can insert our soil bearing capacity. So let's come back to our floor mesh and analysis. If you observe our raft foundation mesh and analysis, it has been ticked as good. Previously it was marked as X, but now it is ticked. So we'll come back here and our soil bearing capacity is 110 kilonewton per meter square. The reason why we are adopting a raft foundation for this very structure is not just related to the soil bearing capacity, but if we intend to use a pad foundation for this structure, we will have pad bases that are co-joining, that are interfering with each other. So a raft foundation is more advisable and economical in situations like that, considering the fact that we should be assuming a pad thickness of 400 mm thick, okay? So in this case, we'll adopt this 110 kilonewton per meter square as our soil bearing capacity, and we'll click on analysis post processes. So you wait for this very stage to load, and here we have our raft that has been analyzed, our raft slab that has been analyzed. All right, so we'll click on this standard contours and we can relate the keys here to these contours, okay? So we'll click on our bending moment on the X direction. You can relate these values, these are the keys to this map. So you can relate the point at which these values are acting on this map, okay? So this is minus 65.5 up to minus 41.5. So it's actually anywhere you see this color of purple, so you can relate it to this map, okay? So this is the maximum bending moment on the Y direction. You can also relate it with this map, with these keys over here. So this is the bending moment on direction 1, direction 2, and we can as well see our displacement under each of these conditions, okay? So this is how our raft will behave under this loading condition, all right, under these moments. So the next is our under the design moments. This is how our foundation will behave. This is how our raft will behave. We can also click on this to seal the various displacement. So let's stop this animation, and at this point is where we can see the area of steel that is required in order to construct this raft slab, okay? So at this very section, if the thickness of your raft slab is not sufficient, it will give you an error message and tell you to probably increase the thickness of that very slab in order for it to be able to carry the load that is coming on it. All right, so if we click on our area of steel required at the bottom, as you can see, you can relate this to this map. Okay, you can relate these values to this map, but the maximum area of steel required at this at the bottom is 2865, and this value is too extreme. All right, because if we bring out our raft, if we bring out our cross-sectional area table, let's bring that out. All right, if we bring out our cross-sectional area and we look at the maximum area of steel required in order to counter our moments at the bottom, then we should be heading on to, this is 2865. Then it means we cannot use Y16. It means we cannot use Y12 anymore. So we have to go with Y16 at probably 75 mm spacing or 50 mm spacing, and this is not advisable. All right, this is not advisable. There are ways you can remedy this even on Prota-Structure. So we also get to look at how you can remedy situations like this. Okay, so you don't necessarily need to construct with Y16 at 75 mm spacing. All right, so our slab did not fail. Then we also have to check the area of steel required on direction 2 at the bottom. So we'll click here. All right, and the maximum area of steel required at the bottom is 2017. So we can also relate that with our cross sectional area of steel. All right, the next is our area of steel required at the top. As you can see, the maximum, which is 1150, is required at these areas. Okay, is required at these areas because this map is what helps you to read where you have these values. So these maximum areas of steel are around the orange and the red zones, while these areas that we have purple can be reinforced with the values around the area of steel around these other numbers. Okay, so the next is the area of steel at the direction 2, also at the top. Okay, so we have one issue to remedy here. The first is to reduce the area of steel required for the construction of this very raft slab. Now the second thing we should be looking at is the soil pressure. Okay, as you can see, we have the maximum soil pressure here at 456, which is currently acting at the edges of our foundation. We can as well reduce this soil pressure that is coming to our foundation because this is actually higher than our allowable soil bearing capacity. So if you take your map to this area, you will see that we have 391 or 4041 is greater than 154, and is actually giving us a warning at these areas. Okay, because these are the values at these areas, which is between this 399 and 456. The 456 is the maximum, while other values that are in orange and red are between this 399 and this 456, which we can actually find at these edges. So as you can see, we have 406, or for this area we have 311 greater than our 154. So this is actually a very risky situation. So how did we arrive at this 154? So if we come to our calculator, do not forget that our allowable soil bearing capacity is 110. Okay, so this 110 was multiplied by our partial factor of safety, and our partial factor of safety at the foundation level is set to 1.4. So we can multiply this by 1.4. So that is how we have 154 over here. But if you have to take our map to these purple areas, let's take our map to these purple areas, the purple and the green zones, or these purple areas, you can see 50 points or 37.024 is less than 154. So this is actually okay. All right, so what we can do is we can help this foundation to spread this load over a larger area. So this will help us counter the first and the second issue. So it will help us reduce the area of steel required for construction due to the fact that the cantilever will also absorb some of those areas of steel. All right, so let's close this up. Let's close this, and we will not transfer our slab strip analysis result. We will not transfer this because we have to make some modifications to the design. So let's cancel this. All right, and we can also, now let's close this. So in order for you to set your partial factor of safety, it all depends on your soil test report. You can come here and come to foundation design settings. Okay, this is your factor of safety of 1.4 that was used to multiply your soil bearing capacity. So ensure the result you are getting from your soil bearing capacity has not been multiplied by this partial factor of safety. If it has already been multiplied by this factor of safety, you can take this to 1, so it takes the existing value. That's just to say you have to understand your soil test. All right, so let's cancel this. Then we'll make modification to what we have done here. So in this case, to remedy this issue, what we need to do is create our cantilevered footing. All right, so to create our cantilevered footing, or our apron as you may call it, we'll come back to slab, or we'll close this, then we'll click on one of these slab, we'll right click, then come to properties, then we'll assume same concrete cover and thickness. We'll come to our loading panel and we'll change this to 0. All right, so let's come back to the general tab, and at the slab type we'll right click and we'll select type 12. Okay, so we'll select type 12. Then the length of our cantilever, which is our L cant, we can click here and we'll take this to 1 meter, which is 1000 millimeters. Okay, so remember your relative level has to be set to 0 because you are putting the cantilever at the base of your beam, not at the top of your beam. So we can draw from here to here and we'll take to this direction, click continue. All right, and let's take a look at what we've modeled so far. So this is our cantilevered footing at the base that can help us spread this load over a larger surface. All right, so let's come to our plan view and we take the properties of this slab and we insert them from column to column points. All right, so we'll click from here to here and take to this direction, same as this. If you find this video helpful at any point, do not forget to like, subscribe, and turn on the notification bell so you get notified anytime we post new videos on our channel. And over here we have the last cantilevered footing. All right, so let's close this up and take a look at what we've been able to achieve so far. So as you can see, we have actually created our raft base. All right, we've actually created our raft base at the bottom of our beams. So this helps us to spread this load over a larger area. Okay, so let's come to our plan view and we have to rerun our Raft slab analysis, our finite element Raft analysis. But before we do that, we'll take out all the earlier modeled slab strip, because our boundary condition has changed from beam and now we have cantilevered edges. Okay, so what we'll do is we'll come to slab strip, and we'll come back to, we'll start from the X direction, we'll come to finite element strip, and in this case we'll be starting from a cantilever to a cantilever. All right, so we'll click here for the X direction and we'll put this here. So we'll also click here and this and this, the last on the, ensure you hold your control button. Then the next is we'll come to the Y direction, still cantilever to cantilever, and we'll draw from here to here. We'll also draw from here to here. All right, we'll draw from here to here. The next is from here to this point. Let's close this. Then we can go ahead and run our Raft foundation analysis. And let's head on to analysis and we'll click on finite element Raft foundation analysis. So we'll click here and over here we'll click on generate model. So you allow it to mesh your foundation level. So we can close this up and allow it to take us to our post analysis processing tab. So this X will be turned to, will be ticked green. Okay, so we'll come back. This has been ticked. Okay, so let's come back to the post analysis tab and we'll take our soil bearing capacity back to 110 and we'll click on analysis post processing. All right, so we'll click on our standard contours. Let's click on our standard contours, and if you observe our movements as well, we'll click on all of this in order to load them to our structure. And do not forget the issue we intend to solve as a as respect to the cantilever we've created. So we'll click here and click on the last one. Okay, so our challenge was our required area of steel. So now if we come down here to click our area of steel required, you can see the maximum value for this area has been reduced. Okay, although the value that will be used in the detailing will be within the range of purple to probably these green zones, because we can rarely see the red zones over here. It could be at just one spot on this very model. It could be at just one spot, but the conventional reinforcements that will be used on the that Prota-Structure we use to detail for us will actually range between these values, but this is the maximum. But even at the maximum, we have 1625 against about I think 28 something that we're having when we've not created our apron or our cantilevered footing. So this is for the direction 1, and we also observe for the direction 2. So the direction 2 value has been reduced to 2153. All right, now the area of steel required at the top This was about 1100 and something, but now we have 393. All right. So this is how you can solve this issue on Prota-Structure while designing. Okay. If you find this video helpful at any point, do not forget to like it, subscribe, and turn on the notification bell so you get notified anytime we post new videos in this series. Now, the last bone of contention for our raft slab before we move on to our beam design, because our slab has to be designed in order to transfer that load to the. So the last bone of contention was our soil pressure. So if we click on our soil pressure, you will observe that the maximum soil pressure at any point on this raft foundation is now reduced to 130 against 400, I think 456 that we had earlier. The maximum value we have towards this zone is now reduced to 130, which is way lesser than our 154. All right, so with this, we can say we've successfully completed the design of our raft slab. So the next, we'll be moving on to designing the raft beams. All right. So let's close this up. And since we are satisfied with the output of our raft foundation analysis, we'll transfer the slab finite element analysis result to our model. So you tick and click on OK. So it will take us back to this post analysis tab and click on transfer foundation beam result. So you click here, then our foundation beam finite element result has been transferred to the model. Then we can click OK. All right. So in order to see the reinforcements that will be used in the construction of this slab, just right click, come to arrange steel bars, then you click on update steel bars. All right. So automatically it will detail your raft base for you. All right. So at this zone we have Y12 at 150. At this zone we have Y12 at 250. Here we have Y12 at 250. Here we have Y12 at 200. We have Y12 at 250. So we've successfully completed our raft slab design. And let's bring out the design reports for the raft slab. So let's come to concrete design. I will click on slab analysis and design. Then we click on design. And as you can see, this is our calculation sheet. Let's save this. This is our calculation sheet. So you have to check your, let's check if we have any insufficient section. So we do not have any insufficient sections over here. To throw more light on this, you can go through our previous video, slab analysis and design. It will throw more light on how you can read this calculation sheet and effect any changes where required. All right, so ensure you have your deflection checks on each of the slabs before you can conclude. So we'll close or we'll minimize this. We'll close this up and we can cancel. So we are finally done with our raft slab design. The next step is going to our beam designs. All right. So to design for our beams, let's come to concrete design and we'll come to beam reinforcement design and we'll click on foundation beams. Remember, not story beams at this point in time, but foundation beams. So by default, all these beams should be failing because we've only transferred the load to the beams and we've not actually designed for them. All right. But before you design, there are few settings you need to make. So those settings, if you click on settings and parameters here, and under this design tab, come to our concrete covers. All right, so the concrete cover for our beams, for the top most part of our beams, we'll assume a concrete cover of 30 millimeter. Then for the bottom of our beams, due to the fact that it will be having a direct encounter with the soil, we can increase this to 50 millimeter, while by the side of our beams we can take this to 50 millimeter, but I prefer taking this to 30 millimeter. All right, so this is the first modification you'll be making before you can design your beams. Keep in mind that if you do not put this concrete cover, a concrete cover of 100 millimeter will be assumed. So by the time you take a concrete cover of 100 millimeter to the left and you take a concrete cover of 100 millimeter to the right, so for the beams of having a width of 230 millimeter, you'll be left with 30 millimeter. All right, so ensure you set this, because if you do not set this, your beam designs will fail. Okay, so the next is we come to the parameters tab. Then what is the minimum steel bar diameter we intend to use for our beam design? We'll leave this at y16. What is the maximum steel bar diameter we intend to use? We'll leave this at y16 as well. Then our web bar. All right, keep in mind that our web bar is not necessarily countering any moments on our beams. It is there to provide rigidity for our beams, to make our beams more compact. So we can go with y12. Let's assume this is the foundation beam we are designing for. This is the rebar diameter, the maximum and the minimum, which has been selected as y16. But these reinforcements over here are our web reinforcement. Okay, so it's not actually the moment is actually acting at the base and at the top, but this is to provide firmness for our beam. So we can adopt y16, we can also adopt y12, but in order to create a very cost-effective design, let's adopt y12. All right, so we'll minimize this and we'll leave this at y12. So our minimum number of hanger bars, we'll leave this at 2. That is at the point where we do not have movements, either at the top or at the bottom zone. Our minimum number of hanger bars should be 2. So the minimum hanger bar, we can go with y16 as well. Then we move on. We leave these other settings as it is. This is the detailing length of our reinforcements. That is the total length of the length of 1 unit of your reinforcement. So we'll leave this as 12 meter, which is the standard. Then our links or our shear reinforcement or our stirrups, we will take the minimum bar diameter as y10 and the maximum bar diameter as y10 as well. Another setting we need to effect over here is our maximum spacings. Okay, so the maximum spacings between our links. Now, due to the fact that this is a deep beam, which the thickness is 1.2 meters, if we leave the maximum spacings between our stirrups or our links to be 300 millimeter, there will be high chances of our beams failing in shear. All right, so we can reduce this to 250 millimeter, so we have a more firm beam. All right, so this is okay. Then we will save this. Yes, and we can now design our foundation beams. All right, so you click on beam design batch mode. Then we tell it to reselect all bars. Okay, so now we are done with the design of our beams. We have some members passing and we have some members failing. All right, so we can remedy this because this is what is involved in your design. So we can now move from the stage of beam design to the stage of beam interactive design. So this is where we have to interact with the beam, know what the possible issue is, and know how we can remedy those issues on our beams. So to go to the interactive design interface, double click on your beam. So if you take a look at the first top bar we have over here, 3y16 has been provided for us to counter the moment at this zone. Why this is sufficient, you also have to observe your extra area of steel provided. All right, so take a look at this value over here. If I increase this, you will see this value over here will change. Okay, so now we have 211. So it is advisable, because our 3y16 is actually sufficient to counter the moment, but the extra we have above this 3y16 is just 10. So if we bring out this steel table, let's assume we have 500, all right, as the area of steel required, and we've provided three numbers of y16. So we'll now have 603 against 500, and that is to tell us that we have 103 area of steel provided as an extra above what was required. Now, if we increase this value to 4y16, while we have the area of steel required as 500, then we have about 304 extra area of steel provided. All right, so this is what this zone is talking about. So if I take this to 4y16, you will see the extra area of steel provided has been increased. So it is always advisable to take your extra area of steel to be above 100, just to cater for uncertainties. This thing over here is very small. All right, so let's take this to 4y16, and at this zone we do not have much reinforcement, we do not have much movement here. So if we take this to 3y16, you will see the extra here is about 603. So this is not cost effective. We can reduce this to 2y16. Then we'll take out this top reinforcement. We'll take out this reinforcement at this support zone. Let's remove this reinforcement here. Then we can minimize this. We'll reduce this and take it back up. All right, so let's deal with the top bar, then we'll come to the bottom bar. All right, so let's finish up with the top bar. For this, our extra here we have 383, which is actually sufficient. For this zone, we have our extra here as 152. All right, what some engineers can do is they can decide to take all the reinforcements at the top zone to be 4y16. Okay, but there's actually no need for this, since you already have an extra area of steel provided, which is actually sufficient. So let's reduce this back to 3 for this span and reduce this back to 2. All right, so now we are done with our top bars. So the next is our bottom bars. Okay, so for our bottom bar, we have 3y16 provided here, and our area of steel extra is 603. So we will minimize this. You can see it's reducing. So let's take this back to 3y16, but we have a supporting bottom bar over here. So what the software is doing for us is, let's take a look at this drawing. Okay, so it is providing another reinforcement at the support zone. Okay, so when we are moving from this span section onto the support section, it is providing another reinforcement here. Okay, so in order to counter this moment. This is not actually required, because the reinforcement we have over here is still 3y16, while the extra reinforcement that is provided for us here is still 3y16. Okay, so what we can do is we can extend this reinforcement to move directly from our span zone onto the support zone. Then it will continue to the other parts. Okay, that means we can have something like this. We can have 3y16 spanning at the bottom, at the entire bottom of this beam. Okay. So let's minimize this. Then we can take out this reinforcement. Don't worry about this. What you just need to do is extend this reinforcement to lap into this other part. Then the second set of reinforcement that is here, make it to lap to the left. So as you can see, we have the same area of steel extra. Okay. So in order to remove this red that is showing here, just reduce this value and take it back up, and this will go out. All right. So we also do the same here. We'll take out this supporting bottom bar. Then we'll increase this to 3y16. Then we'll make it lap on the right and make it lap on the left as well. For this one, we'll also make it lap on the left. Then we'll reduce, just click down and click back up. Okay, so we have this reinforcement. Okay, the next step is we'll take this out, extend this to lap at this zone. So as you can see, let's take this out. So as you can see, we did not have any more issues with our reinforcements. Okay, so let's maintain 3y16 in order to remove this value here. Let's maintain 3y16. Okay, so this is 3y16 at the bottom, 4y16 at the top for the first span of our beam. The second span, we have 3y16 and 3y16 and so on and so forth. Then the next are our web reinforcements. So it has provided 4 numbers of Y12, which is something like this. That provided 4 numbers of Y12 at this web zone. So this is, like I said earlier, this is for rigidity of our beams. So it is advisable to always keep the spacing between this web at, let's say, between 250 millimeter to, it all depends on the thickness of your beam. If you are going as deep as 1.5, then in order to create a very rigid beam, you should be looking at spaces of about 200 millimeter. So how do we come to this 200 millimeter or 250 millimeter? If we take our calculator, and bear in mind that we'll be having, if you are using 4 steps of Y12, we'll be having 1 space here, 2, 3, 4, and 5. Okay, so if we divide 200 by 5, we'll be having the average areas of spacing between our reinforcement, both at the bottom, the top, and the web, at 240. All right, but if we reduce this to 3 numbers of Y12 and we are maintaining a thickness of 1.2 meters, if you take 1200, keep in mind that if you are reducing this to 3 numbers of reinforcement, we will now have 1, 2, 3, and 4 numbers of spacing between our reinforcements. All right, also considering the concrete covers, but we will have 4 numbers of spacing. So if we divide this 1.2 meter by 4, we'll be having the average distance between our reinforcements averagely around 300 millimeter. I would prefer we leave this between 250 millimeter. So let's come back, and if we reduce this reinforcement to 3 numbers, you can see it actually has no effect whatsoever. All right, so let's take this to 4 numbers just for us to have a very rigid beam. All right, then we can click OK. So as you can see, our beam has passed. All right, 4y16 at the top here, then the rest is 3y16. Remember, we can as well take this to 3y16 for it to be a conventional reinforcement, but due to this area of steel extra, we have to take this to 4y16. Now this area that you see that is red over here is actually telling you the size of aggregate that you can use in the construction of this beam at each of these zones. All right, so the maximum aggregate size you can use in constructing this beam should not be anything greater than 28 millimeter. So we are actually very safe because the average diameter of our coarse aggregate is 20 millimeter. So we are actually very safe. So we'll click OK. To learn more about that aspect, you can go to our previous videos on beam analysis and design, and you will see a detailed approach on how you can calculate each of those values. So we'll also make some modification to this beam and other beams. All right, so for here we have our area of C extra as 151, which is actually okay. For here we have 381. This is actually sufficient. Let's take out this extra bar, then we'll increase here to 3y16. We can as well take out this extra. So let's take this down and let's increase this to 4y16. Okay, so 4y16 we provide adequate we adequate to counter our movements at the top zone. So same as this, we'll take out this extra reinforcement, then we'll extend this to lap. We'll take this one to 3y16 as well, extend this to lap, and extend this to lap. Okay, so you can reduce this value and just increase it will take out this value. So let's take out this entirely, extend this to lap both on the left and the right. All right, take this down, take it back up, and we are good to go. The next is we reduce all of this, then we extend this to lap at the left hand side, take the value down, take it back up, and we are good to go. All right, so the next is our web bar. We are still sticking with 4y12, so we are not making any modification to this. Let's save this and reopen. So now we have 3y16 at the top, spanning from here to this place, and for the last beam we have 4y16. Okay, so this is how you can design each and every of these beams on the foundation level. But due to time and due to the fact that we are trying our best to keep these videos as short as possible, we'll also try to terminate at this very point. But this is the ideology behind our design of beams at the raft. So you can go ahead and design these beams and ensure you achieve your desired utilization ratio. To know more about this utilization ratio and the utilization ratio that is advisable for your structure, I'll advise you go to our previous videos on beam analysis and design, and you will see a detailed approach to this. To see our calculation sheet for our foundation beams, just click on this part and it will bring out your calculation sheet. So from your calculation sheet, you can as well ensure you do your deflection checks on each of those beams. You can also check your punching. So this is so let's close this up. So we've gotten the required reinforcement for our beams and the required reinforcements for our slab. So the next check we need to make on our structure is our punching check. All right, so let's check if our structure will be failing in punching, and we'll click on concrete design. Then there is column punching check over here, so we'll click this. Then all the columns will be selected. Then you click on design. All right, okay, so this is our foundation punching checks, and like we said, our beams are there to eliminate our punching stress that is coming from our columns. So if you check, this is adequate, this is adequate. So you can go through this so you can go through this calculation sheet. If there are any inadequate section, this will automatically tell you that this very section or this portion is failing what? In punching. So at this section we'll be rounding up this tutorial, but we just have to cut a section through our slab. All right, so let's come back to our story. So to cut a section, let's click here, then let's cut a section through this point. So you can click on this part, hold your control, then click here, and as you can see, this is our raft. This is our raft. Let's also cut on this other side. So we'll click here and click here, so you can position this here. All right, so this is the base, the apron, or the cantilevered footing. These are our beams, these are the slabs, these are our corresponding beams, and at this junction we can say we've completed the analysis and design for our structure.